In your basic food chemistry course, this is chapter 6. We're going to talk about how do you determine protein in a sample of feed or food. So there's 5 different methods that are normally used to determine protein content. I am most familiar with the first one, which is the Geldahl method. There's also a dye binding method, the Biuret method, the Lowry method, and the ultraviolet method. So we're going to give you some information about those. So the Geldahl method that you can use is one I'm most familiar with. So the principles that go behind this method are start with digestion. So you take a sample and you add a concentration of hydrogen sulfide to it, and then a catalyst. And during this digestion, which is heated during this time, the nitrogen is converted to an ammonium ion. Okay, so we're stripping out the nitrogen out of basically the protein base. Then we're going to neutralize it with NH3 to get, NH3 with N8OH, and then it's going to go through a distillation process with steam of that NH3 and trap it in boric acid. And then it's titrated with hydrochloric acid, HCl, which makes sense, it's what's used in the stomach. And what's going to be resulting of this process is the nitrogen. So basically, the calculation for this method is we're 1 milligrams of nitrogen or percent nitrogen is there per gram of sample. So we have the milliliter of the sample minus the milliliter of the blank. And we have a standard acid that's added, and then divided by the weight of the sample. And so the milliliters of hydrochloric acid is required to titrate that sample solution. So that's the calculation for it. The big disadvantage of using this method is that not all nitrogen that's present is actually protein that's in a product. So you could have some purines, some pyrimidine, DNA, RNA, urea. There's some plant tissues that have greater than 50% non-protein nitrogen. So there's some kind of disadvantages that's going to measure any nitrogen that's there, which, okay, if we're measuring for a ruminant animal, for their feed, that's fine, because they can utilize that nitrogen. Those that are non-ruminant animals are not going to utilize it as much. So, but if we get the percent nitrogen from this technique, then we take it times a factor of 6.25. We know the percent protein in that source. So the dye binding method, the principle is at a low pH, basic groups of proteins are positively charged. These will also quantitatively bind a negatively charged dye. So what are these basic groups? They would include things like glycine, histidine, arginine, and then of course your acid side would be like orange 12. So procedure for this is you mix your protein, your dye, and then you buffer to where you get a pH of around 2. It's filtered or then it's centrifuged, and then you measure optical density of the filtrate. So the optical density dye bound by protein equals basically how much dye is initial, basically compared to how much is left in the filter. So again, this is looking at the percent protein and looking at skim milk, and you can see the reflecting value is basically as protein gets higher through the Geldahl analysis, and that's the other way I've seen it spelled. It just kind of depends. Different ways spell it differently, and sometimes PowerPoint probably auto-corrects it anyway. So if it's spelled differently, that's fine. But you can see the dye solution definitely does change as percent protein does go up. So some factors that influence dye binding determination: number 1, the temperature. Number 2, you're also going to have some non-proteins that are there if they have some nitrogen ability or capabilities to them. What buffers used, and also the protein quality. If it's a good quality protein, it's going to be better for the dye binding method. Low quality protein, not as good. So your Biuret method, basically, you're going to take some ionic copper, Cu, in an alkaline solution form, and basically with the complexity with the peptide bonds, and basically it'll give a pinkish purple color. And then you measure the intensity of that color at 540 nanometers. So you can kind of see if we would plot this on a scale, as protein goes up, the intensity of that color goes up as well, and that's the Biuret method. The Lowry method is probably one of the most selective. It also uses copper in an alkaline solution to form complexity within that protein. This copper is going to go through the catalyst oxidation of the phenol group of tyrosine with a phosphomolybdenic phosphotungstic acid. Oh, those always kill me. But that's kind of how it works, and so it's going to look at the milligrams of protein Gel-Dal analysis, and then you can kind of see as the protein goes up, basically it's going to also select more for the more nitrogen that's there. So when you use ultraviolet absorption or UV absorption at 280 nanometers, this is something that also can be used. So your chromophoric side chains of your aromatic amino acids like tyrosine and tryptophan can be utilized. So when you're talking about absorption at 280 nanometers, it's non-destructive way or means to actually determine protein. So your calculation protein composition is based on how much of that UV light is absorbed in this analysis. The fluorescence method, again, tyrosine is a fluorescent compound, tryptophan is a fluorescent compound, and so what you do is you excite the amino acid at about 280 nanometers, and then you measure emission of that fluorescence at 348 nanometers. And the advantage is it's more sensitive than UV absorption, so the fluorescence is a little more sensitive using this method. You see this with tracking the milligrams of protein per milliliter of solution. You can see that there is a good correlation with the more protein, the more fluorescence is actually measured in intensity. So what is fluorescence and how to measure it? Basically, you have the ground state, and of course then you have the excited state, which we just talked about, and then that actually comes back down. So that emits the radiation or fluorescent back, and basically it decays yields fluorescent at longer wavelengths. So by using a specific wavelength to excite and then measure the output of a specific wavelength, it's pretty specific, and that's why fluorescence is used quite a bit for protein determination. The problem with this model, or method to use, is sometimes there might be some turbidity or quenching, maybe self-turbidity, self-quenching, something like that. So basically you can kind of skew the results. It's also pretty expensive, and quantifications, actually measuring it, is somewhat difficult. But maybe within a sample somebody wants to know what is the actual amino acid profile of this protein itself. So to determine that, you're actually going to have to take that protein and sort it through hydrolysis. So it's usually digested overnight in 6 molar hydrochloric acid at 100 degrees Celsius. And then there's some enzymes that are added to it. And then they'll go through an ion exchange separation to determine the actual amino acids. So this method of ion exchange chromatography is more about basically kind of realigning the amino acids, separating them, and being able to change basically their ion, how they're exchanging these electrons as you change pH. So then they put into a chromatography system, and it monitors basically the moles per liter, of any of these things. So at different wavelengths, we're looking at these ions, whether it's lysine, histidine, asparagine, glutamine, alanine, valine, and leucine, and they're all expressed at different pHs along that scale. So proteins, some important reactions of proteins we need to talk about is denaturation, or denaturation. Basically that allows for changes in the secondary, tertiary, and quaternary structure. And so usually that happens by heat, is probably the most common, but it also can be by heavy metals like mercury. It could be by changing the pH, which is trichloroacetic acid, phosphotungistic acid, things like that. Also salt, it could be sodium chloride or ammonium sulfate. Those also could be used to denature or break down proteins. So some reasons for wanting to break down or precipitate these proteins is one, to purify or to concentrate that protein. Also, it could be just to remove the protein, which could cause some turbidity, may have some emulsion characteristics, or it's just troublesome that we need to identify and remove. So the endpoint manifestation of denaturing these proteins, what happens is you have decreased solubility. You also change the size and or shape of it, but you ought to have some greater reactivity. You have some decreased biological activity like enzymes and immune proteins. You also have increased sensitivity to electrolytes, and also we can do it to alter or change the nutritive value. So what is an essential amino acid? And we will, we cover this a little bit. It's amino acids which the body cannot make or make enough of for protein synthesis due to lack of enzymes. So here's your list of essential amino acids. Sometimes it's 9, sometimes it's 10, depending on what information you use. But histidine, leucine, methionine, threonine, isoleucine, glycine, phenylalanine, valine, arginine, and then occasionally tryptophan. Sometimes say it's essential, some people say it's not. So limiting amino acids is basically what it is. It's the essential amino acid which is lacking in the protein to have a balanced protein overall. So basically what that means is corn, the amino acid that's really not there to be complete for most animals or humans is lysine. You see that's a pretty common one there. And so the problem that comes with that is like for feeding pigs, lysine's the most limiting amino acid for pigs. Pigs got to have it. So a lot of products that would go into pig feed is pretty lacking in lysine, so that has to be balanced in that ration. So cow's milk, potato, chickpea, green pea don't have a lot of methionine. It's a pretty limiting or a pretty lacking amino acid there. In beef, it's valine, and chicken is tryptophan. So next, how do we determine what's a high quality protein versus a low quality protein? And so we can look at it 3 different ways. Is what is the protein efficiency ratio? Number 2, what is the biological value? And number 3, what is the net protein utilization of that protein itself? So what are the measurements of protein quality? For labeling purposes, one really needs to know the protein efficiency ratio. So if your protein efficiency ratio for casein, like 2.5, then the recommended daily allowance is 45 grams per day. If the 0.5 is less than the protein efficiency ratio of 2.5, then the recommended daily allowance is 65 grams per day. So if the PER is less than 0.05, like 20% of casein, then it's not a significant source of protein. So it's all about what is the protein efficiency ratio compared to the recommended daily allowance for an individual. So how does one determine the PER, the protein efficiency ratio? So they take a male lab rat at around 21 days, basically less than or equal to 28 days of age overall, and at least 10 rats per group. They're going to feed a standardized diet containing the salt mix, vitamins, cottonseed oil, cellulose, starch, and sucrose, plus water for those 28 days. They're going to measure weight gain and food intake at regular intervals, not greater than 7 days apart. And then they're going to do the PER, which is basically the weight gain divided by grams of protein in the diet. And it's usually normalized for casein at about 2.5. And then they'll determine protein quality of the sample as a ratio of sample PER to the reference and casein PER. So that protein efficiency ratio basically is going to equal gain in weight per gram of protein eaten. So what that's calculating is how much of that protein is actually resulting in a pound or a gram or a kilogram of weight gain. So this protein efficiency ratio, again, is a number that describes how well a given protein will supply the building blocks for rapid growth. So you can look in this trial, it's a 100% rice product and has a 2.3 protein efficiency ratio. But then if you add the rice at 70% with black beans at 30, it goes to 2.7. But at 50-50, it goes down to 2.6. So you can see the protein efficiency is going down with more of the black bean being added to it. So your corn with lysine or tryptophan, 2.14. If you go back to the corn plus black bean, it's 2.05. So you can look at these and say what's the most efficient type of feed source for actual protein growth. So this is the protein efficiency ratio for some products. You can see soybean, you can see egg. And by most accounts, egg is one of the best proteins that you can have. It has one of the highest biological values. It has a perfect chemical score of 100. So it makes sense that it has a very good protein efficiency ratio, as opposed to, kidney beans not so good, or soybean, that makes sense. So I mentioned biological value on the previous slide, and here it is in an NPU, which is net protein utilization. So the biological value is the retained nitrogen, so nitrogen intake minus fecal and urinary nitrogen divided by the absorbed nitrogen. So basically nitrogen intake minus fecal nitrogen. So basically means within those that have a higher biological value, they're more readily used in the body and less losses of nitrogen go out into the fecal material or byproducts. Net protein utilization is retained nitrogen divided by intake nitrogen. So basically, you're really looking at biological value times digestibility. All right, that is the end of Chapter 6. Complete your quiz in Canvas and any assignments.